Hello, in today's lesson we are going to do the dynamic study of simple harmonic motion. We are going to see what kind of force causes the simple harmonic motion, and we will also make an energetic analysis of it. Let's remember the kinematic equations of simple harmonic motion. They were sinusoidal functions. The elongation was a sine of omega t plus phi. When we derived, we obtained the velocity at omega cosine of omega t plus phi. And if we again derived the velocity with respect to time, we obtained the acceleration minus omega squared sine of omega t plus phi. We can say that the simple harmonic motion is the one whose acceleration is proportional to the elongation, but with negative sign. If we apply Newton's second axiom, force equals mass times acceleration, we can see that the type of force is minus kx, which is what you all know as Hooke's law. Equation of the spring, where the force exerted by the spring is related to the elongation or elongation x caused by the external force, which this time is the weight. On this particular case of the spring, it is easy to observe the characteristics of the force that causes the simple harmonic motion. First of all, we will say that it is a force proportional to the elongation, but in the opposite direction. When you take a spring and stretch it downwards, when you let go, you observe that the force exerted by the spring is upwards, contrary to the direction of motion. Moreover, if you stretch it more, the more intense that force is. Then it is also proportional to the elongation. Secondly, we can say that it is a restoring force which tends to bring the mass to its equilibrium position. When we separate the mass from the equilibrium position on the spring and release it, it tends to go to that equilibrium position. And finally, we will say that this K is a constant of proportionality, which is the elastic constant of the spring and is measured in the international system in newtons per meter. Therefore, the force that causes the simple harmonic motion is of type minus kx. If we equate it to mass times acceleration, expressing acceleration as the second derivative of x, we obtain this expression, which if we order it, gives us this homogeneous second order differential equation. Don't worry, I hope we're not going to solve it here. You'll see that in college. We're just going to check that a solution of type A sine of omega t plus phi satisfies that differential equation. So, to do that, we substitute terms. We have here the second derivative of x with respect to time. In the previous lesson, we saw that if I derive this twice, what you would get is minus a omega squared sine of omega t plus phi. Then I have plus k divided by m, which is this right here, multiplied by xa sine of omega t plus phi equals 0. To make this equality true, we can take this first term, which is with negative sign, and take it to the other part of the equal with positive. Then we observe that in both parts of the equal, I have the sine of omega t plus phi, which I can remove, and an a on each side, which can also be removed, and then we would only have k divided by m has to be equal to omega squared. Then omega has to be equal to the square root of k divided by m. Then the solution to that differential equation is of the type a sine of omega t plus phi with the pulse equal to the square root of k divided by m. Another way to obtain information about the motion without solving the differential equation is to perform an energy study. The mass m that we have at the end of the spring, by the fact of being in motion, has a kinetic energy, which you all know is a mean of the mass times the velocity squared. Moreover, the elastic force that we have just obtained, minus kx, is a conservative force. That is, it derives from potential, and the work it does along a path is independent of the path followed. The work done by the spring as it stretches from 0 at x to a position x is equal to the integral of the differential f of x between these two positions. If I substitute f for minus kx, I get an integral that is immediate, minus k is constant, and the integral of differential x of x is x squared means, which we evaluate between 0 and x and give us, we get that the work is equal to minus 1/2 of kx squared. On the other hand, we can also, we said earlier that kx, that force, derives from potential, and therefore that force we can equal is equal to minus the differential of the potential energy from which it derives. Therefore, we are left with the fact that effectively the work does not depend on the trajectory followed, but only on the final and initial position, right? And if we take as the origin of potentials the equilibrium position, when x is equal to 0, then we obtain that the work is minus the potential energy at x. Equating these two expressions, we come to the conclusion that the potential energy of the spring at a position x is equal to 1/2 of kx squared. Therefore, we have that the kinetic energy is 1/2 of the mass times the velocity squared, that the potential energy of the spring is 1/2 of kx squared, and that the mechanical energy, which is the sum of the two, is equal to this term right here, okay? It's the sum of those two expressions. If we substitute here the mechanical energy, okay, the elongation and the velocity of the simple harmonic motion, we get this expression. If we also substitute this k for its value, we just got that the pulsation has to meet, it has to be equal to the square root of k divided by m, and from there you can clear that k is equal to the mass times the pulsation squared. Well, we substitute that in there, okay? And you could take out then, common factor, 1/2 of the mass times the pulsation squared and the amplitude squared. And we would then be left with cosine squared of omega t plus fi plus sin squared of omega t plus phi, which is 1. Conclusion. The mechanical energy possessed at each instant by a system moving with simple harmonic motion is proportional to the square of the amplitude of the vibration, which remember that it was the maximum elongation. This was A. If we represent the three energies graphically, we can observe that at the extremes, here and here, when the spring is fully contracted or fully elongated, we see that the kinetic energy in blue is 0. Why? We saw in the previous lesson that the velocity at the ends, when it is fully contracted or fully elongated, the velocity was 0. However, when we are in the equilibrium position, the velocity we saw was maximum, and therefore so is the kinetic energy. If we now look at the potential energy, we see that the opposite is true, which is red. At the extremes, here and here, we see that the potential energy is maximum, because the potential energy depends on the elongation. And when the spring is fully contracted or fully elongated, the elongation is maximum. While when it is in the equilibrium position, x is 0, then potential energy is also 0. And graphically, it is very easy to verify that the sum of the graph of the blue curve and the red curve gives us a constant, which is the mechanical energy, and therefore the principle of conservation of mechanical energy is fulfilled. Here, I leave you a summary with the type of force that causes a simple harmonic motion, force equal to less than x, and the expressions of the three energies, kinetic, potential, and mechanical. See you in the next lesson.